Okay. Tomorrow is a holiday for you. Tomorrow also, huh? Holiday. Yeah. School, yeah. Your school has given leave means big thing. How come? That's okay, but yeah, thank you, ma. Thank you. Thank you. உங்களுக்காக தான் இருக்கு. நான் நியாயமா நீங்க கொடுக்கணும். மை டீம் டோல்டு நீ கொடு இந்த வாட்டி. அதனால இங்க வைக்கிறேன். ஐ கான்ட் கம் அண்ட் கிவ் இட். இல்ல வாட் டிட் யூ டு the school? Hmm? What did you celebrate? I could hear some sounds. I could hear. It's backside of my apartment only. So I can hear whatever you people do. அப்படியா? With teachers, பிரணவா பெனால்டிக்கா அப்படின்னா பெனால்டி கிக்கா? ஓகே ஓகே. Right, those are online. Are you able to hear me?
Yes, sir.
Yes, sir.
Everybody is sitting at home. Okay. We'll do some problems. Actually, what did I say today? I told I'll complete AC generator, right? I'll complete this chapter is what I told. Okay. Problems part, we can hold it. So listen. Right. See, officially, this is the last topic of this chapter. Right. So this is going to be the last topic of this chapter, right? In which we'll be discussing about this concept called as AC generator. Right. So now our topic of discussion is about AC generator, right? So what does AC mean here? Here AC means alternating current, right? So it is going to be called as alternating current. And what does a generator mean? Generator is something which generates, right? What is it going to generate here? So generator here is going to be a device, right? So what is this device going to do? This device is going to generate alternating current. So if that happens, you call it as an AC generator, right? So an AC generator is also called as a dynamo, is basically a device which converts. See, for it to generate something, it needs to use some physics principle, right? So what is the principle it is going to use? It is going to use the conversion, right? The principle of conversion of mechanical energy into electrical energy. That is, with the help of mechanical energy, means I'll give you a system. You put that system into rotation or translation, whatever you can do, you do whatever you want. But generate electrical energy and give me. If that kind of a system is existing, then it is what the called as an AC generator, right? So here, the first question I'm supposed to ask is, when I say mechanical energy, right? Right. What does it do? So what is the mechanical energy I'm trying to talk about? So the mechanical energy here is generated due to the rotation, right? So it is generated due to rotation of something, and due to that rotation of, I'll tell what that something is. Due to the rotation of it, we can see that electrical energy gets generated, right? So here, the name generator is a misnomer because it does not generate any energy. So what does it generate? It generates the alternating current, right? And what is it actually going to do? It converts mechanical energy into electrical energy. So if this kind of a system is to exist, right? Let's start asking the questions of what should be the idea behind the design of this kind of a structure, right? So first thing, I know for me to generate current or EMF, right? What is needed? For you to generate EMF, according to Faraday's law, you need a change in flux taking place with respect to time. What flux? You need the change in magnetic flux taking place with respect to time. So if that happens, we can say that the EMF is getting generated. Okay, accepted. If magnetic flux has to change, then all I need is a coil. Because magnetic field cannot be associated with an open conductor. It can be associated only with a closed conductor. So closed conductor is basically a coil. So here I need two things. What is it? I need the magnetic field and I need a coil because I need an area. That is the reason why if you observe the basic structure of how a generator is designed is, it is going to have two magnets, right, which are going to be in the shape of a concave. They are going to be permanent magnets where they have concave shaped structure, so that there is a magnetic field that is obviously going to exist from which pole to which pole? From North Pole to South Pole, right? When it is existing, this is going to be a constant field. So we know one thing, that flux is dependent on three parameters. What is it? BA and theta. It is dependent on BA and theta. So if the flux has to change with respect to time, one of the parameters will change and the other two will be fixed. In this case, if you observe, the magnetic field is going to be a constant because you have used a concave shaped structure to generate that magnetic field. In the presence of it, what we are going to place is a coil. The coil is mainly to have this area. But what is going to be the name of that coil? It's called as an armature coil. So this coil is the one which is going to rotate inside the field, right? So this pink color one is the armature coil. But if the coil rotates, at the ends of the coil, what is going to happen is there will be an EMF generated. We need a source to take it out. See, it is not like it is going to generate the EMF and we are going to leave it further. So whatever you are going to generate, you need to take it out. For that, what we are going to use is, we are going to use two rings, which are called as the slip rings, right? The slip rings in turns are connected to two carbon brushes. Okay. So when these carbon brushes are connected through the load, here the load means electrical load. It can be a light, it can be a galvanometer, it can be anything. But you cannot use a galvanometer because the moving coil galvanometer will not be able to detect AC. Why is it so? We'll see it in the next chapter. Okay. So we'll place some kind of a load here. Right. What is that load called as? It's called as an electrical load. So this is the point through which the output is taken. So if you see, it is a very simple diagram. What is it? We have permanent magnets to generate the magnetic field. We have a coil to have the area, right? And that coil is connected to two rings, and the rings in turn are connected to brushes, and the brushes are connected to the electrical load. This is the simple structure of it. Now, since we are saying mechanical energy needs to get converted to electrical energy, what is happening here is, this coil is the one which is put into rotation. So if you need to put it into rotation, you need to do some work. So by you doing some work, it is going to be in rotation. And all that we are going to see here is, due to this rotation, how is the EMF generated? If at all it is generated, what is going to be the value of that EMF? Is that point clear? So let's see how it works. So in this case, if you observe, the flux is changing not because of B, because it is fixed. It is not changing because of the value of area, because it's, in this case, it's still a rectangular coil. But it is changing because of the orientation. In the sense, when this coil is in rotation, the angle made by the aerial vector with magnetic field is always changing with respect to time. Right? So this is one case where the flux is changing due to the orientation. In all other cases, we would have seen either magnetic field will change or area will change. See, for example, when we discuss motional EMF, in motional EMF, magnetic field was constant, but the area was changing. You remember that the conductor was moving. When the conductor moved, that rectangular area was changing. In this case, what is happening? The area is fixed, but the orientation is changing. Okay. So having said this, now let's try to understand what is going to be the value of the EMF that is going to get generated in this case. So if I take this theta and I say that this coil is rotating with an angular velocity omega. Let's say the coil is rotating with an angular velocity omega. Then what is going to be the relation between the angular displacement and omega? Is what the question is. So if you observe, theta will be equal to omega naught into t plus half into alpha t square. Like how you use S is equal to ut plus half t square. I'm using theta is equal to omega naught into t plus half alpha t square. But remember, here the coil is rotating with constant angular velocity. Having said that, the angular acceleration is 0. Right, then what is going to be the value of theta? Then theta will be omega into t. Take this, put it here. So when you do that, you will get flux is equal to BA into cos of omega t. So this is going to be the flux generated by one turn of this armature coil. I'm using the word coil. It is not a loop. It should definitely be a coil. One loop cannot produce that much value of current. Right? So if I take n number of turns, what is going to be the total flux? It will be n times BA cos of omega t. Right? Now, all that I'm going to do is, instead of delta phi by delta t, which is average value, I will differentiate it. Because the flux in this case is a perfect function of time. So when I differentiate it, I find d phi by dt, then I'm going to get NBA into what is going to be the derivative of cos omega t. It is minus sine omega t into omega, because I'm using the chain rule. Right? So d phi by dt is equal to minus NBA omega sine omega t. Am I right? So I combine this omega with NBA. So it is minus NBA omega into sine omega t. But d phi by dt is nothing but negative of EMF. Because EMF is equal to minus d phi by dt according to Faraday's law. Right? So I'll cancel this minus and this minus. So what am I going to get? I will get E is equal to NBA omega into sine omega t, and this is going to be the value of the EMF that will get generated due to this device, right? And let me explain it. This E is equal to NBA omega sine omega t is what is called as the alternating voltage. Alternating voltage. Okay. So this NBA omega can be written as a value E naught. I'll tell you what that E naught is. And the sine omega t is left as it is, and this is going to be the EMF. Now, if you observe this, since I call this as alternating voltage, this EMF is what is called as the instantaneous voltage. So why we call it as instantaneous voltage is because by you substituting different value of time inside this, you will get different value of EMF. Okay, I'll rub this way. Right. So this is called as the instantaneous voltage. This E naught is what is called as the peak value. It is called as the peak value, or it is also called as the amplitude. It is also called as the amplitude. And omega is what is going to be the angular speed. So in this case, this angular speed is the one which decides the frequency of the alternating voltage, right? And t is obviously going to be some instant of time, right? And remember that this equation is going to be the building block of your complete 7th chapter. This is the equation we'll use throughout the 7th chapter. You should not get a doubt of where did we get the equation from. It is coming from the output of an alternating generator. Okay. Is it clear till this step? Okay. So there is one small point to be explained, but before that, you just copy this. Yeah. So online, could you understand?
Yes, sir.
Yes, sir.
Okay. Keep writing. One point taking question. Thing is, you understood what is instantaneous EMF and this peak value, right? Now, when you plot a graph showing the variation of so when you plot a graph showing the variation of EMF and time, right? We know that EMF is a function of time, right? But the function is varying according to the trigonometric ratio sine. So we already know the graph for sine, right? So how is the EMF going to get generated? It will be something like this, right? Where you have something called as a positive cycle and you have something called as a negative cycle. This positive plus negative cycle put together is what is called as one full cycle, right? Like this, a pattern keeps on repeating itself. It keeps on going because it's a periodic function. Now, what is this E naught? This E naught is going to be the amplitude. What do I mean by amplitude? It is the maximum value attained by this EMF in either of its directions. In the sense, this is also going to be E naught. This is also going to be E naught. So, this E naught combined with the sine function is going to be the name of this graph, which is E, which is given by the equation E naught sine of omega t. Am I clear? So, the other point that we can make a note from here is E naught into sine of, how can you write omega in terms of time period? So first thing, we should know what is the time period. So time period is basically the time taken to complete one full oscillation, right? So the time taken by this wave to travel from here to here is what is called as one time period, right? And what do you mean by frequency? It is not the angular frequency. I'm asking about frequency. The number of oscillations that have taken place in one time period. Or you can say the number of oscillations that are completed in 1 second. That is more appropriate, right? So if you look at it, can I write omega as 2 pi into f into t, where f is the frequency, right? Or this also I can write it as E naught times sine of 2 pi into frequency can be written as 1 by time period. So 2 pi by capital T into t. So what I'm trying to tell you here is the same instantaneous value of EMF can either be written in terms of omega or f or capital T, and all the three mean the same. So are you able to understand? So here, what is happening is, observe. Okay, so I'll tell you first listen. So what is happening here is, when I say E is equal to E naught sine of, I'll take this expression 2 pi by capital T into T. Okay, I'll take this one into the consideration. So if you observe the graph, if you observe the diagram initially, the magnetic field is like this. The magnetic field is in this way. Let's say your hand is like this, the coil is like this, right? Now tell me, initially when the magnetic field is in this direction and the coil is kept like this, What is the angle between the magnetic field and aerial vector? It is 90. So when the coil is like this, the aerial vector is like this and the magnetic field is in this way. So the angle between them is 90. Initially, what is the flux associated with it? 0. So at t is equal to 0, the amount of flux associated with it is 0. So from here, let's say it is rotating clockwise. So when it is rotating clockwise, after some time, it would have come like this. So when it comes like this, the aerial vector of this coil is in this direction and the magnetic field is also in the same direction. So what is the angle between them? 0. So the flux has actually changed from 0 to, when the value of angle between the flux, value of angle between the magnetic field and the area is 0, flux is going to be maximum. So initially, what was the flux? 0. From 0, it went to maximum. Now, what will happen? The coil is still going to be in rotation. From here, it is going to take a turn and come like this. When it has come like this, it has completed half a rotation. So magnetic field is still in the same direction. When the coil is like this, what is the aerial vector? It is in the downward direction. So magnetic field is like this, aerial vector is downward. What is going to be the angle between them? Again 90. So what has happened? From maximum, again the value has gone back to 0. So after coming here, it will take a turn like this and come in this way. When it comes in this way, what is the angle between the aerial vector and magnetic field? Aerial vector is this side, magnetic field is this side. It is going to be 180 degrees. So cos 180 will come. Cos 180 is negative. So after coming from here, right, what will happen? Again, it will come back to the top position. So when it comes to the top position, again, the value will come back to 0. So what is happening is, at t is equal to 0, what is the value of theta? If I take this to be the direction of magnetic field, and if I take the aerial vector in such a way that the area is like this. So initially at t is equal to 0, the area is in the plane of the magnetic field and the aerial vector is perpendicular to the magnetic field. So at t is equal to 0, can I say theta is equal to 90 degrees implies flux is equal to 0. At t is equal to, how much time will it take for the coil to rotate from here to here? It will take 1/4 of the time period. So 1/4 rotation, 1/4 rotation, 1/4 rotation, and last one is 1/4 rotation. So there are totally 4 1/4 of rotations. So to go from here to this position, it will take a time of t by 4. So from 0 to t by 4, when the coil has got rotated, what is the value of theta? Theta is 0 degrees. In this case, flux is going to be B into A, which is going to be maximum. So at t is equal to t by 2, how much rotation would have got completed? See, in 1/4 of time period, 1/4 of rotation is over. In half of time period, half rotation will be over. So theta is equal to how much? Again, it will be 90. So in this case, what is going to be the flux? 0. So at t is equal to 3t by 4. Where will it be? So 3t by 4 means it will be like this, right? Equal to 180 degrees, which implies flux is equal to, it will be minus BA, and minus BA is going to be the minimum value. At t is equal to capital T, what will happen? Theta will be equal to 90 again. So phi will be equal to 0. So what is happening here is, between 0 to 1/4 of time period, the value is increasing from 0 to maximum. So there is a change in, right? So there is a change in flux here. It is an increase in flux. Here, what is going to happen? There is again a decrease in flux. Again, there is a decrease in flux, and there is an increase in flux in the downward direction because it is going from 0 to minimum value. Again, from minimum, it is going back to 0. So everywhere, if you see, there is a change in flux taking place, and due to this change in flux only, there is a EMF that is getting induced. But what we are supposed to do now is, the reason why I considered this expression is, at this instant, I will be able to find the instantaneous EMF. With the help of this equation, I'll be able to find the instantaneous EMF as E naught sine of pi by capital T into what should I substitute in the place of small t? I should substitute 0. So what is it telling us? Initially the voltage generator is 0. That is why the graph started at 0. Okay. And what about the EMF here? So E is equal to E naught into sine of 2 pi by capital T into what should I substitute the T by 4. So T and T will get cancelled. I'll have E naught sine of 2 pi 2 pi by 4 is pi by 2. Sine pi by 2 is 1, which is E naught. So what is going to happen is at T by 4, the value of EMF is E naught. So what will this value be? It will be T by 2, right? So what you can do is, if you substitute T by 2 and C, when you substitute T by 2, you will get E is equal to E naught sine of 2 pi by capital T into T by 2. So T and T are gone, 2 and 2 are gone. Sine pi is again a 0. So like this, if you keep on writing, right, you will get the value of the instantaneous EMF at that point. And with that also, you can analyze this graph. Similarly, if you substitute 3t by 4, right, if you substitute 3t by 4, you will get 3 pi by 2. 3 pi by 2 is minus 1. So this will be minus E naught. And when you substitute back t, again it will be 0. Okay. So this is how the equation can be used to solve problems also. If suppose they suddenly ask you what is the value of the EMF at some instant t by 3, all that you need to do is in the place of t, substitute t by 3 and you will get the answer. Is it clear? So first draw this graph and make a note of that values. You're feeling cold. Switch off the AC. Done with this graph? Let me know once you're done. Done? So with this, the chapter is over. Okay. But I told you I'll teach you one concept, right? I'll explain that. Shall I close this? So, see. Not sure if you're able to hear. See, listen. This concept that we are going to discuss is called as eddy currents. EDDY, obviously currents. Okay. So in this concept, what we are going to see is how a paramagnetic or a diamagnetic substance is going to respond to the external magnetic field or a sudden change in the magnetic field. Okay. So the setup that they have here is this plate you're able to see here, no? The flat surface that is there. Right. This plate is half ferromagnetic, that is, it is made up of steel, and half it is made up of copper. Right. So tell me one thing, if you take a magnet and place it near the steel, what will happen to it? It will get attracted. Whereas if you place it across copper, it should not get attracted because copper is a diamagnetic substance. Okay. So when there is a sudden change in magnetic flux taking place within a diamagnetic or a paramagnetic also, see what is going to happen and how they are going to respond. So the plate he has in his hand is a copper plate. It is not sticking, right? So when this magnet, this magnet is released from a certain height, what is happening to it? It is swinging, right? Why is it happening? It is because of the gravitational force. So it is acting like a simple pendulum, right? It is put into oscillation. But if you take the same magnet closer to that plate, see what is going to happen. Okay, now it got hit, but see what is going to happen. Did you observe what happens? So there is a copper plate. Had it been iron, it would have got stuck. It is a copper plate. When this is coming down due to gravity, as soon as it encountered the copper plate, it is coming to instant rest. Okay. They are not in contact. Okay. So now he has a copper plate, right? These two are magnets. Those dotted parts are there. No? So when the copper plate is dropped across this railing, what do you think will happen? When this copper plate is released from this position, when it is dropped, what do you think is going to happen to it? It is obviously going to travel down due to the gravitational force, right? So just to see or show you what will be the consequence if the experiment fails, is going to use that carrot and show you. Okay. Just for you to understand the impact. So if at all there is a mistake, right? See what will happen. So what he is doing is he is moving the magnet down. See what is going to happen. His hand is replacing the carrot. You saw what happened to that carrot, right? So if science fails, he cannot have his hands. At least, see, he kept the magnet there, right? His hand is there. See, it will get slowed down. So why it is getting slowed down is because of this current called as eddy current. So still we are sticking to the basic only. What does this whole chapter tell you? It tells only one thing. What is it? For you to generate EMF, there should be a change in magnetic flux. So you release the plate from the top. There is no magnetic field associated with it because it's not encountering any magnet. But when it is traveling and coming here, there is a sudden change in magnetic flux taking place within the copper plate. So when there is a sudden change that is taking place, there is an EMF induced in the plate itself. And due to that EMF, there will be circular currents that will get generated in the plate itself. Those circular currents are what are called as eddy currents. So if you see the main application of that eddy current is, you saw right what happened. It slowed down the system. So you can use it in braking system. Wherever you want magnetic braking systems, you can think of using it. See, imagine you're in an exhibition, okay? Or you're in a theme park. Let's say you're going in a roller coaster. So obviously it is going to go down and go up, right? When it is going down, had there been only the presence of gravity, right? See, let's say at this, when it is going horizontally, which is not going to happen for a longer duration, you know that. It will either go up or down. That's right? So let's say there is certain speed associated while it is going in the horizontal direction. What do you think will happen if the same speed is maintained even in the downward direction? When it is going in the horizontal direction, let's say there is a speed of v value that is maintained. Let's say 20 kilometer per hour. When it is going down also, if there is 20 kilometer per hour maintained, what will happen is due to acceleration, due to gravity, that speed cannot be maintained at 20, it will rather go up. And imagine yourself traveling in the downward direction with a greater speed. The first thing is you will face an injury. But it is not possible for us to for our body to take that amount of shock because there will be a change in velocity taking place. So the only thing is it has to get slowed down when it is going. There should be a control taking place. So to control that, what they can think of is this kind of a system where they will make use of the eddy currents and provide a magnetic braking system. They will not completely cut down the speed, rather they will try to reduce the speed to have a controlled motion. You're able to understand? So this is one such fact. Now, to understand this better, right? I hope you got some perspective out of this. Right. Now what we'll do is add, sir. Nothing can be done. So now you'll understand it better, see.
This magnet, south pole here, this magnet. So there's a fairly uniform field in between here. I think
Are you able to see the cursor?
Here, where it is steel, it will stick to that probably strong. So I have here is blue. Okay, so aluminum is parallel, so that it is. So it's not really attractive to that.
1 minute, sorry. So in the previous case, what you had was a diamagnetic substance, which was copper. Now what you're having is, you have a strong magnetic field produced between these two poles. Now inside this magnetic field, what will happen if you project a paramagnetic substance? See, if it is a diamagnetic substance, let's say you're throwing an iron nail, what would have happened? The iron nail would have either got attracted right or to the left. It will definitely get attracted for sure, right? Whereas when you pass a paramagnetic substance, observe what is going to happen. So the paramagnetic substance that is being used here is an aluminum. Is aluminum.
So this is like the north pole here, this magnet, south pole here, this. So there's a fairly piece of steel here, or a piece of steel, it will stick to that probably strong apart. So what I have here is a piece of wood. Okay, so aluminum is paramagnetic, so we don't get a so it's not really attractive to that. Okay, so I also get
So there is aluminum plate that is going to be used in 3 ways. One is, you saw it right, it was a complete plate. The second is with slots, and the third is a comb-like structure, right? All the three will be led to oscillate between the magnetic poles. See what is going to happen.
this one, and this one slots go all the way to the bottom. So there's no connection along the bottom. These are put in here will bring this swing.
And this is oscillating because of gravity. See what happens. You would have observed by now. So it is coming to instant rest. So let's see what will happen when this slotted plate is pushed. So this is also stopping, but it's slightly going and coming back, right? It's not instant. What do you think will happen to this? It should not stop.
Okay, what is happening is that as this one is swinging into the.
So you tell me one thing, as this is going into the magnetic field, right? What is happening there? There is a change in magnetic flux taking place. When there is a change in magnetic flux, what will get induced? EMF will get induced. So if there is EMF induced, there will be current that will be induced. So where will the current flow in this case? The current, see, these are all metals. Though they are diamagnetic or paramagnetic, they are still metals. Means they are good conductors of electricity. Though they are going to carry the current among themselves. But this time, it is not going to be in a circular, it's not going to be in a loop outside the conductor or something. Within the conductor itself, there will be small slots of current that will get generated. Those small circular currents that are getting generated is what is called as eddy current. And I'll show you how you can validate it. See, suppose, let's try to take that experiment and put it in this form. If there is a magnetic field which is into the plane, you tell me which pole are we acting as? I'm standing here and looking at it. I'm acting like the north pole. So this is going to be the south pole. Now, so this is the plate which is trying to enter. So when the plate is trying to enter, the flux is increasing or decreasing? Flux is increasing. So if there is an increase in flux, what pole will get generated? Will it be the same pole or opposite pole? It will be the same pole. So coming from the beginning, I am the north pole and this plate is facing me. Flux is increasing. So the same pole as what I am should get generated. What pole am I? North. So there should be a north pole that is getting generated. So due to north pole, what is going to be the direction of current? It will be in the anti-clockwise direction. So there will be small values of anti-clockwise currents that are flowing in this plate, and those small currents are what are called as eddy currents. Observe. So this is the way currents will flow. So that is why eddy current is also known as, there is something called as, this word is not much used. It's called FOCAULT, Foucault currents. Eddy current is a textbook term that is being used. They either use Foucault current or they also use the word circular currents because these currents are always in circular loops. Are you able to understand this concept? So this thing is the one which you will see it in the next chapter in a topic called as transformers. So in the transformers, right, there is one type of a loss which is called as eddy current loss, and this is what they're trying to talk about. So why they call it as eddy current loss is because when these currents are getting generated, you know, when current is going to flow through a resistive device for a longer duration, heat is going to get generated. Are you able to understand? These are all small currents, but when you talk about transformers or something, the value of current is going to be very high. When high value of current is going to flow, then you know that there is going to be loss of energy in the form of heat. So that's why they call it as eddy current loss. For you to understand the term, I had to explain this. Am I clear till this point? Right? So this is all about eddy currents, and this chapter is over. Okay. So I just wanted to give one heads up. Okay. I'm actually, see, there's only an experiment I'm trying to do. Okay. See, you would have seen by now, my idea is to connect physics or science for that matter to real world and teach. So I thought today's real world that I can connect, at least what I use in my real life is somewhere in shopping, for example. Let's say you're asked to shop on Amazon, whatever product you're going to buy, right? How many of you actually read the description? Do you see the price tag or you see the description and you read the whole description? No, right? No worries. Do you read everything? See, suppose I ask you, what do you buy? What do you generally buy on Amazon? Books. You buy books, sir? Are you sure you read the description? You're using a book, right? Can you tell me there is something called a GSM with respect to a paper? Have you heard of it? What is it? But you have seen that. Do you know what GSM that value is? No, right? You know what is GSM? Those are online. Do you know what is GSM? It's called gram per square meter. It's called gram per square meter. Gram is a unit of mass. Square meter is a unit of area. Mass per unit area is called as GSM. I can use gram per square centimeter. It is called surface mass density. So that is why when you look at the papers, right, especially depending on what paper you want to buy. Suppose I give you a task. Let's say I'm asking, suddenly I have a request, I need to print an agreement. You see these rental agreements and all, right? That you have seen it? Yeah. So I'm sorry. It's okay. I'll clean it. That's fine. So you've seen those rental agreements, right? The bond papers are there, no? They are of different GSMs. The one which is at the top will be somewhere around 100 GSM. That's why it's thick. Okay. And similarly, you look at the papers which are used inside, they'll use green colors, right? They are called as illegal papers. There'll be some other GSM. Okay. So my idea is to spread the knowledge because she used a word, what did she use? Surface mass density. Actually, it's a part of your syllabus. How many of you know that? That's used to calculate the center of gravity. It is there in your 11th standard. But I'm sure that nobody teaches like that. So the experiment I'm trying to do is, see, it's not only physics, okay? My interest is in all subjects. Math, I'm not good with bio, I'll tell you. I'm not good at all. I'm very bad. You ask me a question, I don't know. But okay, chemistry, at least I can try. Math and physics, you know me already, right? So I want to connect them to these kind of shopping aspects or something that is related to your real-time applications. You're able to understand. So I've actually taken the data also. See, for example, you're studying something here, you know, this mutual inductance and everything. That also has a real-time application. I'll show you. You will understand what I'm trying to talk about. Just a small concept, and then we'll wind up. I'll tell you why I'm trying to do that also. You know what? Any idea about what this device is? This device is a transformer. Because when we say transformer, you always think of the ones which are outside your house. Not necessary. Even these chargers do have transformers in them. They're that small. Those are all electronic transformers. Because, can you tell me what is the amount of voltage that is coming out of this place? Somewhere around 230 volt. If you want the proof, you can look at that stabilizer. You're able to see some number. Is it varying 220 to 230? That is an AC voltage. If that amount of voltage directly goes to my laptop, first thing I can see is a bomb blast. Okay, it cannot work. If I directly take a device, take a wire and directly connect it, then I could have devised a charger like that. No, why do they need something like this? So inside you have a transformer, means the 230 volt is first brought down to a certain value of how much that this can withstand. After bringing it to that range, you will have a fluctuating DC. I'll tell you what a fluctuating DC in semiconductors. That is stabilized to DC, and then we'll start using it. But I'm sure none of you will know this. Okay, it is actually a part of your syllabus, but it's not taught. Why I took this one is today I wanted to explain something, and the reason I asked you for description is those who are online are able to see.
Yes, sir.
See, I think this is the one. I actually wanted to take a pic. So you're able to see something here. What is the name of this? It's a pattern name. It's a power transformer. So input voltage is how much? The 230 volt AC is the input that is given. And what is the output voltage? It is 1202 something what they have mentioned. 12 volt. Okay. So output current is how much? It's 1/5 ampere. It is 0.2 ampere it is coming. Actually, to tell you the fact, 1 ampere is enough to kill us. We deal with problems, right? 1 ampere is sufficient to kill us. Because you calculate the amount of electrons that will flow into your body, it's that dangerous. Because when we are doing problem, nobody 10 ampere problem, they'll put 10 ampere and all, no chance, will burn into ashes. Okay. So you're able to understand. So I was actually looking at these things, and this is also something I wanted to prepare and make a series. Okay. So now I'll tell you why I'm telling you is, you can give me some points of your area of interest on which I'll make a video. These are all the things. It is my idea because this can be related to your syllabus. So I'll give you an idea of what I'm asking is, see, let's say you're good at some sport. Let's take this paper cup itself. Okay. You saw, right? It is bending and all those things. This also has a GSM. You go and next time when you buy dress, right? If you're buying a top or you're buying jeans, you look at a parameter, there will be a GSM associated with your clothes also. That decides the thickness of your t-shirt. that decides the thickness of your shirt or jeans. So more is the GSM, obviously more strong it is going to be, right? So you can choose that. If you want a winter clothing, obviously GSM should be more. So that's what the logic says, no? But I want to put this in your mind in a different perspective. Now, if I was checking about AC today, because I was checking for these things, I was trying to calculate the electricity bill. There they will give you some values. I'll tell you all those things. So based on that value, if you have AC at your home, right, you can actually help your parents to understand if the current bill is right or wrong. Government is cheating these days. I faced that problem. You can actually validate it. You will understand if that is really worth, or you can at least check for 2 cycles. That is what is called as data analysis. அதுக்கு பேர் தான் இப்போ டேட்டா சயின்டிஸ்ட்னு சுத்திட்டு இருக்காங்க. All that you need to do is take 2 months of data, validate it and put it. Verify பண்ணுங்க. புரியுதா? So you need not wait till you go to engineering and learn all these things. These are all day-to-day life skills. Correct? I think it is needed for you to live at least. You need to know how the current bill is calculated, right? How many of you know? They use something called as units, no? Have you heard of that? இவ்வளவு units of current ன்னு சொல்றாங்க. என்ன யூனிட் அது? As a physics student, what unit? You should know what it is. It's kilowatt hour. That's what you learn it as commercial unit of energy, right? That's why they ask a question of 1 unit is costing 1 rupee 50 paise, means for 30 days, how much is going to be the bill? That's a problem, but you can do it for your real life itself. No? So if you're able to connect all these dots, I feel you can learn better. So that is why today I got a thought. I will do a mini series based on how to use shopping to understand science. But I need your help to understand what topics you want me to do. Puriyada? Anything is fine. So now I'll keep that suggestion box there. Whatever is there in your mind, you can think and do it tomorrow. I'll keep that suggestion box there. Can be anonymous also, I don't mind. Or you want to give the name, I'll give the credits, it's fine. So that others can learn from it. It can be anything. இப்போ நான் சொன்னேன் நான் maths, physics, chemistry, anything. இப்போ இதுல physics மட்டும் இல்ல, there is something math also that is related. இப்போ நீ ஒரு AC ஓட ஸ்பெசிஃபிகேஷன் போய் பார்த்தனா, there will be mass that will be given, there will be dimensions that will be given, length, width and depth ன்னு ஒன்னு கொடுப்பாங்க. So depth na ulle எவ்வளவு தூரம் போகுதுன்னு அர்த்தம். அதை பிரித்து you can understand whether that will fit in your room or not. You can calculate it. No, you can use your common sense and think, this is not going to work in this place. I need it at a certain height. I need this angle. Everything you're learning, you can think in those perspectives. I'm not saying you go mad thinking like that, but it's something like your observation can be better. I'm not saying get into the subject and go mad. No, that's not what I'm saying. For survival, okay, it's a life skill, right? So அதனால that's what எது வேணாலும் இருக்கலாம், என்ன வேணாலும் இருக்கலாம். இந்த ஸ்டைலஸ் பத்தி இருக்கலாம், பென்ட்ரைவ் பத்தி இருக்கலாம், anything. I want to buy something, I'll just try to make a video on how what questions you're supposed to ask before you buy something. Why iPhone is better than Android? What kind of sensing they're using? Why are those people fighting? Why Samsung iPhone is fighting? So you can actually do a comparative study. I'm not saying I'm not doing an ad promotion or something here. It is only to explain the science behind it. My job is only that much. Okay. Anything of your interest. So think, and tomorrow I'm expecting some inputs from you. Can I? Right? That will be the best gift you can give me on a teacher's day. At least post teachers, I don't. Only you have to study. Second is, you have to work with me. Okay. Yeah. So those are online clear.
Yes, sir.
Okay. You also come up with ideas.
Yes, sir.
Yeah. See you guys.
Thank you, sir.
Yeah. Thank you.
Thank you, sir.
Yeah.